Okay, so for today, we're gonna talk about section 4.3, the monotonic function and the first derivative test. Okay, so before we talk about those definitions, I'd like to look at a graph of a function here. And in this graph, it actually include all the information points in 4.3. Okay, so first of all, let's take a look at it here. Now, this is the function f of x. Okay, it's defined under the closed interval from a to g. Okay, and also you can see that I labeled a couple of points on this function. And let's see, guys. Let's maybe use this marker, trying to see that. You can tell that at point D, we function have its absolute maximum value, right? This one not work well. Let's see if I can get another. Maybe this one. Okay. And x equals a, it can attain its absolute minimum. Okay, absolute minimum. And also, you can tell that at the point B, f prime of b is 0, right? And also, we know that this is a local maximum. Okay. And at point C, clearly you can see that f prime of c equals 0. This is a local minimum. Okay, local minimum. At point D here, since you can see, guys, if you look a little bit carefully, there is a cusp at point D. So that means the derivative evaluated at D does not exist. Okay, so f prime of D not exist. Okay, okay, and at point E, so f prime of E equals 0, and this is a local max. Okay, local max. And at a point F, almost there, right? So if you can see that f prime evaluated at f equals 0, so I probably should use a different notation, but let's use it at this time. But also see that there's no extreme value here, okay, right? So it's not a local max, it's not a local min. Okay. So A and G are the two endpoints. So what we can tell? Also, guys, based on the definition of the critical numbers, right? As you can tell that B, C, D, E, F, they are actually all critical numbers, right? Critical numbers. And as you can see that, critical numbers, sometimes it can be local max, local min, or neither, okay, or neither. So this is what we already talked about from 4.1 and 4.2. But now let's think a little bit more. You see, guys, if we want to look at this part from A to B, okay, from A to B, and you can tell that if I, let's see, draw some, the slope of the tangent lines, okay, right? So all the tangent lines. Do you agree that on this interval from A to B, and the slope of tangent lines, at any points on this interval is positive, right? Is positive. And also, do you also find that as y-x goes bigger, right, from a to b, become bigger and bigger, the corresponding function, do you agree, it increases, right? In other words, it climbs up. Okay, so under this situation, we have a name, we call that, okay, on the interval from a to b, fx is increasing. Okay, increasing. And how do we measure that? As we just discussed, do you see that the slope of the tangent line at the given point, right, on the interval from a to b, which is the derivative, right, of the function. So as you can see that if we claim that a function it is increasing on this interval from a to b, it's equivalent to see that, okay, the derivative is greater than 0. Okay. In other words, when we get that the derivative is greater than 0 on interval, we can get the conclusion function is increasing. Okay. Similarly, on the interval b to c, right? So we have another name, it's called decreasing. And as you can tell, guys, the corresponding slope of the tangent line between these points is all negative, so meaning derivative is less than 0. Okay, and also from C to D, right, the interval, it's, I use a notation here, okay, it's increasing, and I think I accidentally forgot one point here, maybe we call this point, maybe we call H, okay. Point H, and at point H, it's a local mean, right? F prime at H is 0, it's because it's a critical number. So you can see that on the interval from D to H, function is decreasing, and the derivative is less than 0. From H to E, increasing, okay, increasing. And let's continue. From E to F, the function actually is decreasing, right? And interestingly, for here, guys, you can see from F to G, and then the function is also decreasing, okay, decreasing. So this is other concepts, okay, increasing, decreasing. And, when a function, it is increasing on one interval or decreasing on one interval, we call this function is monotonic, okay, which is here, monotonic. And okay, so that's the first half part of this section. And the second part is talk about the first derivative test, okay. And we can also talk about the first derivative test in this part. As you can see, guys, you see, let's look at it here. We know that at a point B, we have a local maximum, right? And look at the left side of the point B. The function, it increases. And then right passing the point B, the function is starting to decrease. So it's kind of going up and going down, right? It will form a local maximum. And correspondingly, you can tell that it's increase, then decrease. So that means, mathematically, if on the left side of B, the derivative is greater than 0, increases, and then on the right hand side, f prime is decrease, then it's gonna form a local maximum. Okay, so this is pretty easy to understand. And we can also look at point C here, the function is decreasing and then increasing. In other words, at this part, the derivative is less than 0, and then at this part, the derivative become greater than 0. So it's going down and then climb up. So it's a form like like a valley, right, of between mountains. So it's called a local minimum, okay? And similarly at point D, right? So it's derivative is greater than 0 and the derivative is less than 0, local max, right? Well, of course, it's an absolute max globally. And at H, you have decreasing, then increasing, you have local mean, increasing, then decreasing, local max. And for here, guys, you can see that it's decreasing, then decreasing, so there is no local extreme value there, right? Because there's no changing, right, about the monotonic property, so that's the basic idea of the first derivative test. It says like this, if you have a critical number and on the two sides of this critical number, the derivative it changes. Either is the derivative is positive, changes into negative, that means it goes up, and as it goes down, you're gonna have a local maximum. And if it's on the left hand side, it's the derivative is less than 0, which is going down, and then after that the derivative become positive, going up, then you're gonna have a local minimum. Okay, so that's everything about the first derivative test. So now let's maybe look at one examples, so you can see, okay, all the things. Okay, so I don't know. So let's see if we have, let's see, fx equals I don't know. So x cubed over 3, c minus 5 x squared over 2, right? And then let's see, plus 6x, and then I don't know, plus 7. Okay, plus 7. And then the problem is that okay, find the increasing, let's see, decreasing intervals, and the local extreme values. Okay, if any. Okay, if any. And if I didn't, let's call this example 1. Okay, if the problem didn't specify the interval, and also the function is a polynomial, so by default the domain is all round numbers. Okay, so that's the playground, all round numbers. And the problem have two tasks: increasing, decreasing interval, and also the local extreme values, if any. Okay, the progress is very, very straightforward. Okay, so just starting to do this answer. First of all, let's try to figure out the derivative of this given function, which is based on the power rule, give us is x squared, right? Minus 5 plus 6. Okay, plus 6. To find the derivative is actually to figure out the critical points for this given function. So as you can see that the derivative is also polynomial with second degree, right? Polynomial, and there's no values can make the derivative undefined. Okay, because when we try to figure out the critical points, you have to consider about there is one option is certain point will make the derivative equal 0, and there is a second case is there are certain points, and those points the derivative does not exist. Okay, in our problem the second case does not exist. Okay, so we will consider about the first part, which we are trying to find the critical points will make the derivative 0, that is x squared minus 5x plus 6 equals 0. And this is the second order equation, right? Quadratic equation, and you can either use a quadratic formula or factor it, right? In fact, you can do this, right? Very easy to be factored, and you can solve that x equals 2 and 3. Okay, 2 and 3. So those are the two critical points. And so this is step 1. Step 2, what I'll do is, this is what I usually like to do. You know, I want to draw a real line, and I would like to label the critical points. And as you can see that those two critical points partition my domain into 3 pieces, right? The first part is from negative infinity to 2. Second part is from 2 to 3. And third part is from 3 to, not 4, to positive infinity. Okay, to positive infinity. And let's do the other side. Okay. Okay, so right now I'm going to start to list the table here. Okay, so from negative infinity to 2, from 2 to 3, and then from 3 to positive infinity. Okay, I'm going to list the s here, x here, and then we're going to have the sign of x prime, the first derivative, and then okay, so remember the original problem is x cubed over 3 minus 5x squared over 2 plus 6x plus 7, okay, and the first derivative is x squared minus 5x plus 6. So right now, this is what are we going to do? Okay, those we plot those two critical numbers, partition my interval into 3 pieces, which is here, and then start to list the table here. And this is what we call the point testing technique. Okay, what I'll do here is I pick a random point from each interval. For example, on the interval from negative infinity to 2, you can pick any numbers, okay? And again, when you pick these numbers, pick the easy numbers, okay? If it can be an integer, pick an integer. If there is 0 there, pick 0. You know, just okay, follow those simple rules. From negative infinity to 0 is the best option, okay? And then from 2 to 3, well, I don't have, you know, there is no integers between 2 to 3. So I'll just pick the middle number, okay, 5 over 2. And from 3 to infinity, let's pick, maybe pick 4 here, okay. So the next step is you're going to evaluate those values at the first derivative. Okay, it's not the original function. Evaluate at the first derivative and then find the sign. Okay, whether it's positive or negative. Okay, let's do that. F prime of 0, which is 0 minus 0 plus 6, so it is positive. So the sign is positive. Okay, and F prime evaluate 5 over 2, which you're gonna have. Here is 5 over 2 squared minus 5 times 5 over 2 plus 6. Okay, plus 6. And this is 25 over 4 minus 25 over 2 plus 6. And you can let all of those 3 to have the same denominator 4. very easy to calculate, which is 25 over 4 minus 50 over 4 plus 24 over 4. And to the very end, you're going to have it's negative 1 over 4. Okay, so apparently this is less than 0. The sign of the derivative at this interval negative. Why? Because again, guys, this number is random picked. Okay, so and then f prime of 4, which is 4 squared minus 4 times 5 plus 6. So you can tell this is 16 minus 20 plus 6, and then you're gonna have this as 2. It's positive. This is greater than 0. So now we pretty much have everything. Why? First of all, you can see that the increasing interval is from negative infinity to 2 and 3 to positive infinity, right? Why? Because the first derivative is positive at those intervals. And from 2 to 3, it's decreasing. Okay, it's decreasing. Meanwhile, at those two critical points, and you can see that the function actually it's increasing and then decreasing, right? So at x equals 2, you're going to have a relative maximum. And from 2 to 3, it's decreasing, and then from 3 to 8, it's increasing. So you can see that you're going to have a local minimum at x equals 3. So let's write our conclusion here. So this is the conclusion. The increasing interval, pretty small here, okay, which is from negative infinity to 2, union 3 to positive infinity, okay. And then the decreasing interval is from 2 to 3. Okay. And at x equals 2, you have a local max. At x equals 2. At x equals 3, you have a local minimum. Okay, so we complete this whole problem. So that's pretty much everything in section 4.3. It is very straightforward, and I hope you enjoy this, and see you next time.